It actually represents the distortion which is present on a plane in 3 dimension in a given crystal is represented by Burgess vector. This also we are going to read. So these are the contents we are going to study in this chapter. Classification of point defects, Schottky defects in metals and ionic crystals, Frenkel defects, then again one-dimensional defects which are line defects, screw and eddy dislocations, Burgess vector. So these are the contents we will be reading in this chapter. If you want, you take the screenshot. Otherwise, I give 1 or 2 minutes just to note down, because what contents you are going to read, you should know. So write the orders. Please open your book, because some definitions and some diagrams you should draw in the today's session. Once you draw it on the book, probably you can register. That is the motto. Otherwise, in the classroom, anyhow, will be giving regular running notes you have to write, but in the online mode, just to copy this. Classification of point defects, then Schottky defects in metals and ionic crystals, then Frenkel defects, line defects, screw and eddy dislocations, Burgess vector. Please note down the contents of second chapter, Crystal defects. Shall I proceed? Anyone, please? Did you copy?
Yes, sir.
Yes, sir.
So I am changing the slide. So as I said, actually in the basic definition we have discussed, the solids are classified into crystalline solids and amorphous solids. And the crystalline solids in the definition, according to the definition, if the atoms or molecules are arranged in a regular periodic manner throughout the crystal in the 3-dimensional space, then it is called as a crystalline solid. So in most of crystals, what we assume is the space in the 3D lattice, that means which has an identical environment. Each and every atom of the crystal or molecule can be fixed so that there is a regular arrangement of molecules or atoms, and it is continuous. Along, if you take along x-axis, y-axis, z-axis, this pattern is continuous, and this is possible only in an ideal crystal. So in the first diagram, you can see an ideal crystal. All atoms are perfectly arranged in 3 dimensions. This is a 2 dimension, but the same can be extended to 3 dimension. So in an ideal crystal, the atoms or molecules are packed very perfectly. There is a regular periodic arrangement of atoms or molecules in an ideal crystal. But coming to the real crystals, and this is not possible, at least in 1 dimension or in some points, there are certain irregularities and impurities are present. And these are called as crystal imperfections. So in an ideal crystal, there is no impurity, there is no irregularity, everything is perfect. Each and every lattice point is occupied with an atom which has identical environment. But it is an ideal crystal. But coming to the real crystals, in real crystals, of course, at certain extent, some periodicity will be maintained, but in the 3-dimensional space, some irregularities and impurities are present. And these are called as crystal imperfections. And these irregularities, they influence the electrical, mechanical, magnetic, and structural properties of crystalline materials. So, in an ideal crystal, what we have discussed with the unit cell and the lattice parameters, all they are by taking a symmetric pattern, so such that the arrangement of atoms are perfect. But in real crystals, at least in some areas and in some directions, there are certain irregularities or deviations of it. And these are called as crystal imperfections. and they influence the properties of crystalline materials like electrical properties, mechanical properties, some magnetic properties, structural properties, all this. So in the right side, the second diagram you can see, so there are certain deviations. Some vacancies are there, some missing of items will be there, a line is missing, it's not in a perfect order like that. So some irregularities, impurities are present. These are called as crystal imperfections. So how they are classified, what are different types of crystal imperfections? This we are going to discuss in this chapter. That is 1 minute. It's cutting into the time. So the crystal defects are basically classified into four categories. The first one they are called as point defects. The same are also called as zero-dimensional defects. And the second one line defects, which are one dimensional. You know, line is along one line, along one direction, one dimensional defects. And third one surface defects. Surface area is two-dimensional, so the same are also called as two-dimensional defects. And the fourth one, they are called as volume defects. Volume is a three-dimensional concept. So these defects are called as the three-dimensional effect. That means they extend in all the three directions. So the crystal defects or crystal imperfections or impurities can be classified as point defects, which are also called as a zero-dimensional defects, then line defects, which are one-dimensional defects, and the third one surface defects, they are two-dimensional defects, and the fourth one they are volume defects, which are three-dimensional defects. Please note down this. Crystal defects are classified as you write all the four. We will discuss thoroughly all these point defects, line defects in general. Only surface defects and volume defects they are not in the syllabus. So we will confine to point defects and different categories of point defects and a little bit of line defects. We are going to study in this chapter, but you should understand this. You write down. Crystal defects are classified as the four categories. One fine day I'll ask the notes. That time you should be able to focus randomly, not when I get doubt. Please copy this. Is this clearly visible now? This slide? Someone?
Yes,
Respond?
sir.
Okay.
Yes, sir.
Please copy this. Did you copy? Shall I go further?
Yes, sir.
So, as I said, the crystal imperfections or defects are classified into four categories. Point defects, zero-dimensional, line defects, one-dimensional. Third one, surface defects, two-dimensional, and the volume defects, three-dimensional. Again, point defects, sub-classification is also there. The point defects, which are zero-dimensional defects, they are again classified into four ways. First one, vacancies or shorty defects. Second one, interstitials or Frenkel defects. And the third one, they are called as compositional defects, and in some books it is given as impurities. So the third category is compositional defects. The subcategory, again, these are classified into substitutional impurity and interstitial impurity. And the fourth one, electronic defects. So again, these point defects, they are classified into vacancies or shorty defects, interstitials or Frenkel defects, third one compositional defects, and the fourth one electronic defects. So again, these zero-dimensional defects, they are broadly classified into four groups. And coming to the second one, line defects, they are classified into two groups. One is edge dislocation, another one is screw dislocation. This also we are going to discuss in this chapter. And the third one, surface defects, again they are classified into four groups: trailing boundaries, thick boundaries, swing boundaries, and skating faults. So these are the four types of surface defects. Just we should remember this, it is not there in the syllabus. And the final category, volume defects, they are classified into cracks, and the second one, voids or air wells. It's a three-dimensional phenomenon. So in this way, Again, the crystal defects, and there are four types, and in each type, again, a subclass is there. Point defects are classified into four categories: vacancies, interstitials, impurities, and electronic defects. And the second category, line defects, they are classified into edge dislocation and screw dislocation. We'll read these two thoroughly. And the third one, surface defects, we have four types: grain boundaries, field boundaries, thin boundaries, and stacking faults. And the fourth category is volume defects, which is a three-dimensional phenomenon. In this, you have cracks in voids or air bubbles. So this is the classification of crystal defects. If you want, just to take the screenshot. No need to write. Only you should write these two only. Point defects, they are classified into four categories. Line defects. These two only you write it on paper, and remaining you take the screenshot. I'll give 1-2 minutes because we should remember these two. Again, point defects are classified into four categories, and line defects are categorized into two ways: edge dislocation and screw dislocation. Please note these two: zero-dimensional defects and one-dimensional defects. Up to this, is it clear? What is the difference between ideal crystal and real crystal? And what are imperfections present in the crystal? How they are categorized? And what is the subclass? Shall I repeat this once? Anyone? Respond, anyone? Did you copy? Anyone?
Yes, sir.
Is there any doubt here up to this? Shall I proceed?
Yes, sir. You can proceed.
Right. Now coming to, as I said, point defects are also called as zero-dimensional defects, and they are imperfect point-like regions in the crystal. You can't actually, they don't have any physical existence you can imagine because the size is less nano size like that, but there are certain deviations. So you can't tell them they are present in the along x-axis or y-axis. That's why these are called as zero-dimensional defects, and they are imperfect point-like regions in the crystal. And these point defects, they are classified as, just now you have copied all these: vacancies, interstitials, or some books it is given as interstitials. Both are same. And the third category, impurities, and the fourth one, electronic defects. So again, point defects, these are zero-dimensional defects, and they are imperfect point-like regions, actually, which is not having any physical existence, but they will be in large number in certain areas. Uh, but you can't say they are in the existence is little bit ambiguity is there, but they influence the properties of crystals. That's why zero dimension you can understand. It's like vacuum only, but there is some impact. So these are called as point defects. That means there is no instrument to measure that one initially. Actually, you can't find out the position of this defect present in a given crystal. Again, these are classified as vacancies, interstitials, and impurities, and electronic defects. This only you have copied. Now we'll discuss one by one vacancies. So coming to the first category, vacancy. A vacancy implies an unoccupied atom or ion position within the crystal. So in the diagram, you can easily see actually blue color, the circular lattice points are there. All atoms are arranged accordingly. A perfect arrangement will be there. But in the third row, you can observe one atom is missing. So this is a vacant position. So these you can call as simply empty atomic sites. No atom or ion is occupying this lattice point, which creates certain distortion in the crystal. So these are called as vacancies. So vacancy implies an unoccupied atom or ion position within the crystalline plane, and they are simply empty atomic sites. So some places are not lattice points are not occupied by the regular atoms or ions. So they create certain distortion, and these are called as crystal defects, which are called as vacancies. And generally, these vacancies they occur because of the imperfect packing during original crystallization. Because you should fabricate crystals, synthesis crystals. During this process, some order will be missing, so that one lattice point cannot be occupied in the micro level, and also because of the vibrations atoms. At the time 0 Kelvin, it is a perfect arrangement, but getting 0 Kelvin is not possible practically. So, because at a higher, relatively high temperature, because the atoms absorbing some thermal energy, they vibrate from their mean position so that they can be displaced from the lattice point, so that a vacancy also created. So this is the basic reason, so that in some crystalline planes, some empty atomic sites will be there. And ionic vacancies, if an ion is missing in the given crystal plane, then these are called as Schottky defects. So this is the first category in point defects, which is vacancy. So vacancy implies an unoccupied atomic or ionic position within the crystalline material. So empty atomic sites can be called as vacancies. They occur because of the imperfect packing during original crystallization, or due to the thermal energy which is supplied to the atom. They may displace from their mean position, so that some vacancy can be created. And the ionic vacancies, they are called as Schottky defects. You take this first diagram. This diagram you should take, and one atom should be missed in the atomic region. Take this diagram. Is it clear? Vacancy. Please take this diagram. Roll number 83. You're copying. Please respond. 83. Unmute yourself. Is there 83? 88. Roll number 88.
Sir, actually, I came to Hyderabad yesterday, sir. My copies are at my home. To take books, I came, sir.
Okay. Yeah.
So right now, I've taken the screenshot as a copy, sir.
Okay. So you are moving. This is mobile class. You are moving somewhere, keeping your mobile in the pocket, and you are getting attendance. You may get attendance, but you should,
I'm
you
taking
should
it,
get
sir.
marks also. Okay, na? Okay. Shall I proceed for the next one? Need to copy? Anyone please respond?
Yes, sir.
170?
Yes,
You
sir.
are there? Now the second category, it is interstitial cysts. And this is another crystal defect which comes under this point zero dimension defects, which we have discussed the point defects. And this defect arises when an atom or molecule or an ion occupies a definite position in the crystal lattice that is not normally occupied. That means actually each and every atom should be associated with the lattice point. But in this case, it is interstitial. It occupies between the regions of two atomic planes. And you can observe a perfect crystal in the first diagram. They are arranged regularly. But here you can see an atom, it is occupying a definite position which is generally not occupied by the atoms, like this. So this is called as interstitial. This also influences the structure of a given lattice plane, and also the properties of materials. All can be decided because it occupies a indefinite position. Generally, it is not occupied by the regular atom. So here in this interstitials, the atoms or ions they occupy vacant positions or void spaces between the atoms of the crystal, as you see. So ionic interstitials and the ionic interstitials are called as the Frankel defects. Ionic vacancies are called Schottky defects, and ionic interstitials are called Frankel defects. So the second category in the point defects, they are interstitials. Is here an atom or molecule or some ions they occupy in the irregular positions, which is generally not occupied by a regular atom. So this causes certain distortion in the crystal. This is called interstitials. So in general, these atoms occupy vacant positions because between two layers some gap will be there. They occupy that position or white space between the atoms of the crystal. And ionic interstitials are called Frankel defects. And you take these two diagrams also. For a perfect crystal, each and every lattice point is occupied with one atom. But here, an extra atom is occupying a void space. Please note down this diagram and you take the screenshot of these points. These two are clear now. First one vacancy, second one interstitials. Vacancy is empty atomic site. The lattice point is not associated by an atom or ion. So it's a vacant position will be there. Here, a irregular position can be occupied by an atom, which is called as interstitials. Shall I proceed? Anyone? You.
Yes, sir.
Yes, sir.
Yes, sir. Proceed, sir.
Right. And the third category in point defects, it is impurities. The same are also called as compositional defects. So impurities give rise to compositional defects. Generally, these impurities they occur in all metallic, covalent, and ionic crystals. And these impurities they play very key role in certain processes such as diffusion of atoms and the phase transformation. That means solid phase to liquid phase to gaseous phase. Like that, they change the basic property of the material, and also they influence the electrical and thermal conductivities, etc. Sometimes deliberately some impurities can be added to get certain properties. Simply in the intermediate you have studied when a trivalent impurity is added or pentavalent impurity is added, so that you can fabricate N-type and P-type materials and you can construct the diodes. So these impurities they influence the electrical, thermal, and magnetic properties of materials. In addition to the diffusion of the atoms in a given crystal structure, the phase transformation of the crystal, all this. And impurity means a foreign atom is present in a given crystalline material, which is generally not belonging to that particular crystalline solid. Let us example you take NaCl crystal is there. So you should have sodium and chlorine atoms or molecules. But suppose some magnesium or some another is quantity of that is present in the given NaCl, then it is called compositional defect or impurity. So which is not belonging to that particular crystal. A foreign element or foreign atom is present in a given crystal, then it is called as an impurity and it gives rise to certain compositional defects. So in all materials, crystalline materials like metallic, metals, covalent, and ionic crystals also, these compositional defects are possible. They are playing very key role in solid state processes such as the diffusion of atoms, the phase transformation, the proper electrical behavior of materials, thermal conductivity, magnetic properties, all they can be influenced by these impurities. Again, these impurities, they are classified into the first category they are called as a substitutional impurity, and the second one they are called as interstitial impurity. In the table, first beginning table, you took these two. So first again these impurities they are called as substitutional impurity, and the second one they are called as interstitial impurity. A substitutional impurity, it is a point imperfection, and it refers to a foreign atom that occupies or replaces a parent atom in the crystal. So you can see the first diagram. So all are with blue color. Actually, the crystal is made up of these compositions. But you can observe a foreign atom which is colored with red. It is occupying a regular atomic size. So this defect, this is called as a substitutional impurity. So composition defects are impurities. If a foreign atom occupies a regular position within the given crystal, then it is called as a substitutional impurity. And the second category is interstitial impurity. If a foreign atom occupies a void space or irregular position in the given crystalline plate, then it is called as an interstitial impurity. Both are small sized atoms will come into our zero dimensional defects only, but this is the difference. In the first case, if the foreign atom occupies a regular position in the lattice, it is called as a substitutional impurity. If an atom occupies an irregular position or void space, then it is called as an interstitial impurity. So these are the two categories of compositional defects of impurities. You take these two diagrams. If a foreign atom occupies a regular position, it is substitutional impurity. If a foreign atom occupies an irregular position or void space, then it is called as an interstitial impurity. Note down this two. Is this clear, this concept? Compositional defects?
Yes, sir.
Please note. Diagrams for practicing sake, because you can take screenshot, I know, but again you see with your eyes only. But for the exam to reproduce, once you write it on paper, I think it will be convenient for you. The red colored one you mark it as name it as substitutional impurity, and this pink color one in the second case you mark it as interstitial impurity. You can observe it is occupying the in between two perfect atomic regions. It's generally not occupied by the atom in the second case. No need to count the number of circles, randomly you take 3 or 4 please. Shall I proceed further?
Sir.
Shall I change the slide?
Yes, sir.
And the fourth one, in the point defects, the fourth class is electronic defects. So these electronic defects generally they occur because of as a result of the errors that present during the charge distribution in crystalline solids. So you have a positive charge and negative charge. So during this, what happens because of the properties, electronegativity and electronaffinity properties, what happens? The sliding of these atoms or atoms takes place. They cause certain disturbance in the material, and these are called as electronic defects. So these defects, that means only charge carriers which contains certain charge. So they are free to move in the boundaries of the crystal throughout the crystal, and whenever you apply certain electric field, and the movement of these defects contribute for the electrical conductivity. So in the absence of the field, the charge distribution is asymmetric, and it will be there. It impacts the electrical properties of materials, but in the presence of external electric field, it is significant. So these charge carriers can be acquire a velocity so that in one direction they can be accumulated, will be given to certain electrical conductivity. All positive charges will be accumulating at one phase and negative charges in the other phase, so that which causes certain electrical potential, and in the presence of the external electric field, some electric current can be generated, which contributes for the electrical conductivity of the material. So these defects, these are called as electronic defects. Sometimes deliberately these are added so that the actual crystal structure can be breakdown, and they contribute for the conductivity. So case by case, it will change how it impacts the conducting behavior. But in general, during charge distribution in the crystalline solids, some errors exist. So it will not be perfect. Positive and negative ions will be placing at the same vicinity. It's not like that. Because of that, some distortion occurs, and some extra charge carriers will be there in the given crystal. They move freely in the boundaries of the crystal, and in the presence of the external electric field, the movement of these defects will contribute for the electrical conductivity of the material, and these are called as electronic defects. This is the fourth category. So coming to the basics, what I have explained in an ideal crystal, the atomic arrangement is perfect in all respects in 3 dimensions, and it is having periodic arrangement of molecules or atoms, and it is continuous throughout. But practically, once you grow the crystals, once you synthesize the crystals, it is observed that some irregularities and impurities are present in the crystals. So these irregularities are called as crystal imperfections or crystal impurities, and they affect the electrical, mechanical, structural, and magnetic properties of crystalline materials. So in an ideal crystal, arrangement is perfect, but in real crystals, some distortions will be there. If the distortion is very minute, then they are called as zero dimensional defects, which are called as point defects. Along a line, along one direction, if the defects are occurring, then they are called as one-dimensional defects or line defects. If it extends to two-dimensional, then they are called as surface defects. If it extends to three dimensions, then these are called as volume defects. So in a broad way, they are classified into zero-dimensional, one-dimensional, two-dimensional, or three-dimensional, or point defects, line defects, surface defects, and volume defects. Again, they are subclassified into point defects. They are classified into vacancies or shortly defects. Then interstitials or Frankel defects, impurities or compositional defects, and the fourth one, electronic defects. Again, the second category, line defects, they are classified into edge dislocation and screw dislocation. Coming to the third one, which are two-dimensional impurities known as the surface defects, they are classified into grain boundaries, tilt boundaries, pin boundaries, and stacking faults. Only just you remember the names. We are not going in deep of the all above. And the fourth one, they are volume defects. They are three-dimensional impurities present in a given crystal. They are classified into cracks, second one, voids or air bubbles. So this is the broad classification of defects present in crystals. And coming to point defects, as I said, point defects are classified into vacancies, interstitials, impurities, and electronic defects. And a vacancy, it implies an unoccupied or atom or ionic position within the crystal. That means in a regular atomic arrangement, one place is missing. So these empty atomic sets are called as vacancies. And generally, these vacancies will occur because of the imperfect packing during the crystal growth or original crystallization, and sometimes because of the temperature variation. The 0 Kelvin perfect arrangement will be there as the temperature rises. Due to thermal energy, some vibrations of atoms will occur. They may displace the atom from its regular position. So a vacancy will be created. And an ionic vacancy is called as a Schottky defect. We calculate the concentration of Schottky defects. Derivation is a little bit later. And this is the diagram. In the diagram, you can observe that one position is not occupied by a regular atom. This creates an impurity, imperfection in the crystal, which is called as vacancy. And coming to the second one, it is an interstitial system. So this defect occurs when an atom occupies a definite position in the crystal that is generally not occupied by a perfect crystal. That means between two atomic regions, an atom will be occupying. It's not a regular lattice point. So this type of disorder is called as interstitial system. And in this, atoms generally occupy the vacant positions or void spaces present between atoms of the crystal, as you can observe in the diagram. And ionic interstitials are called Frankel defects. So this atom, orange colored one, it is occupying the void space. There is no lattice point actually, but it is occupying this position. This type of defect is called as interstitials. And coming to the third one, They are called as impurities or compositional defects. These impurities give rise to certain compositional defects in crystals, and they occur in all metallic, covalent, and ionic crystals. And they are very crucial in deciding the electrical behavior, thermal conductivity, and the properties such as structural properties, thermal properties, and also the phase transformation of the given crystal. All these can be decided by the impurities which are present in the crystal. By the sometimes without any external source impurities will be there. Sometimes deliberately impurities are added to certain materials so that you can alter the properties, tailor the properties. So both ways you can use, and because there is an advantage, perfect crystal and irregular crystal, both we should use both for certain engineering applications. And these impurities, again, they are classified into the first one it is called as substitutional impurity, and the second one is called as interstitial impurity. And substitutional impurity, it is a point imperfection, it's a zero-dimensional defect only, and when a foreign atom substitutes or replaces a parent atom in the crystal, that means a parent atom is missing and a foreign atom is present in the regular lattice site, then it is called as substitutional impurity. In the diagram, the red colored atom, it is a foreign atom. It does not belong to the original crystal, but it is occupying a regular position. This type of defect it is called as a substitutional defect or substitutional impurity. And the second category, it is interstitial impurity. A foreign atom, it occupies an irregular site or void space in the given crystal without disturbing any parent atom. Then it is called as an interstitial impurity. Here, a perfect arrangement of green colored atoms are there. A pink colored foreign atom is occupying in the void space. So this type of irregularity, this is called as interstitial impurity. In this way, the compositional defects they are classified into substitutional impurity, and the second one interstitial impurity. And the fourth one in point defects is electronic defects. They occur because of the errors present during original charge distribution in crystalline solids. So NaCl minus you should have, but during the crystallization, more number of positive ions will be there. So it disturbs, it unbalances the electrical behavior, and they move freely in the boundaries of the crystal, causing certain distortion. In the presence of the external electric field, this movement is significant, and which contributes to the conductivity of the material in one particular direction. And these impurities or imperfections, they are called as electronic defects. So in this way, the point defects are classified into vacancies, interstitials, compositional defects or impurities, and the fourth one, electronic defects. So these are the four categories we have discussed in the today's class. First one is what is the crystal defect, how they are classified broadly, like zero-dimensional, one-dimensional, two-dimensional, three-dimensional. Again, the subcategory also we have discussed. And the first case, point defects, the four categories, like vacancies, interstitials, impurities, and electronic defects, we have discussed in the today's class. If you have any doubt, you can ask. Shall I continue? Shall I stop today? What do you say? Okay, I'll take attendance for today, and you prepare notes for this, what you have learned today. You have any doubts? Up to
No, sir.
Is it clear now? So here, first one, two topics you can understand very easily, but there are three big derivations of it. The carrier concentration of Schottky defects in metals and ionic crystals, two derivations are there, and the Frenkel defects, calculation of Frenkel defects, three derivations are there. Basing on, you should have certain knowledge on this differentiation, integration, and sometimes some probability loss. Whatever is required, I'll explain. What is required for physics, I'll explain that, and I'll do the derivations, even PPT also. So if you, and you have to practice those three derivations, and only line defects, only surface level will be reading. What are split dislocations, screw dislocations, and the Burger's vector. Only qualitative analysis, there is no derivation for that. And next class, probably I'll take 1, 2 derivations you should do, and one derivation we have to do at your own. Then we'll go for, I need 2 more classes, two end of classes to complete this chapter. And once the first unit is completed, we'll see how I'll take one repetition class, If you have any doubts, you can interact with me. And after that, we will proceed further. And meanwhile, if we got the almanac, then we will announce the internals. Most likely in the second or third week of February, it looks like. But you have to see. And
Sir,
what is
any information about reopen of the college?
state government has taken a decision, should take a decision, man. And second wave, some are saying second wave, but some positiveness is also there because of these vaccines were available. Most likely, there is
Yes,
some
sir.
pressure on the government also. Many states have opened because online is only the alternative. It's not a perfect procedure, even for because you're in the Google Classroom. I am in the Google Classroom. I am delivering the content. How many you are receiving? Because there is no eye contact, you can't assess the student. So from your side, from my side also some, but there is no alternative since 6 to 7 months. We hope after Sankranti, probably our chief minister will give some guidelines. Isman industry will release some almanac. Then we can plan. But they have to decide. We are not deciding factors. Some colleges, autonomous colleges, they are planning, but how far they will be fruitful.
Already opened, sir.
For fourth year, exams are going on, but regular classes I doubt. Officially, and classes are not they are not conducting officially.
Yeah, universities are open, sir.
University, even we are also in the college, man, but students are not coming. I am
No,
taking
sir.
class.
Students only I am saying, sir.
Students are coming in our Telangana.
Yeah. Yes, sir.
Are you sure?
Yes, sir. My friend Malaredi University.
Malarity and autonomous. Malarity, no. Maybe some second, third year teacher autonomous, but they should follow certain protocols. Violating protocols, they can't. We'll see after Sankranti. Most likely, we may have physical classes. Let us hope. So
Sir,
after this,
Sankranti holidays how many?
no man, no, as per 13, 14, only 2 days as per state government because our college will follow state government only. And 9th, 10th, anyhow holidays, second Saturday and Sunday. So 11th, 12th, they are working this. 15th, college has to decide. Kanama, if some were celebrating Kanama, it can be compensated by another Saturday or something. Principal has to take a decision. To take a decision, we'll see. But 13th, 14th, 9th, 10th are holidays. It will be informed to you. Don't worry. Okay? I get this here I'll stop. Some are attending at 110 for attendance sake. Okay, respond for the attendance.